Let's go ahead and get started. So just a couple of administrative announcements. So as we discussed earlier, there will be a makeup class tomorrow. It'll be same bat time, same bat place. You guys are too young to get that reference. As last week's makeup lecture. So that is at, I have no idea. I totally forgot. 4 p.m.? I think it's at 4 p.m. In the piano room, which is Rutherford 211. So as I mentioned earlier, I'm going to have to miss 3 lectures later this semester. We've now, with this one tomorrow, made up 2 of them. We can decide whether we need to make up the 3rd, or maybe I'll get some exciting, special, secret, surprise guest lecturer to tell you something interesting. No? Can we do both? Yes? Sure, we can do both of them. Unfortunately, I had a planned secret, special, surprise guest lecturer, but that guest lecturer is out of town on all of the days that I'm not going to be here. But I'll figure something out. That'll be exciting. Let's see. Did I have any other announcements? I have the next problem set up here for any of you guys who didn't pick it up last time. It's due not next Tuesday, which is a break, but the following Tuesday. But it's a little on the longer side compared to some of the earlier ones, so don't leave it until the last minute. Third announcement. Graded problem sets are available for pickup in the box outside my office. I haven't been bothering to bring them down to hand out in class, since I figure most people would see them there and just pick it up when they turn in their problem set. But if you haven't picked up your problem sets from there, please go ahead and do so. If you have any questions about the grading or anything or details of the problem sets, you can ask the TAs. They're the ones who graded them. Okay, good. Let's see, I think that's it as far as administrative stuff. So let's go ahead and do some physics. So last time we met for the first time the Einstein field equations, which are the equations of motion of general relativity. They're a set of 10 second-order nonlinear differential equations for the components of the metric of space-time. And they're important enough that I will never miss a chance to write down the field equations. So here, G mu nu is the Einstein tensor, which is a linear combination of the Ricci tensor and the metric, which involves various second derivatives of the metric, first derivatives of the metric squared, inverse metrics, and is an all-around rather difficult quantity to deal with. And then, as a source term for this equation, we have the stress tensor T mu nu. Looks like I forgot a nu there. What is the stress tensor T mu nu? Well, morally speaking, it's the symmetric tensor, which is made up of the relativistic generalization of the notion of energy. So in Minkowski space, we have 10 geometric symmetries of spacetime, and correspondingly, there are 10 conserved quantities, which are known as, which are packaged into the symmetric 0-2 tensor we call the stress tensor. And I gave a loose definition for the stress tensor. Well, not so loose, but a not particularly helpful definition for the stress tensor last time, as the flux of P mu across a surface of constant x nu. So it involves various energy and momentum densities and shears, intuitively speaking. And one of the things that we're going to encounter today is a rather different and I think much more practically useful from our point of view way of thinking about the stress tensor. And also, my point of view today is that we derived Einstein's equations last class based on general considerations about what sort of reasonable equations of motion we could write down. And today I would like to give an alternative and equally valid way of deriving Einstein's equations and arriving at them as the correct equations of motion for the curvature of space-time in general relativity. So that's really our goal today. It's to come up with a second independent way of understanding the origin of Einstein's equations. And it's a way that it's probably, well, I don't want to say it's better or worse than the way that we encountered last time, but it's different and equally important. And it provides us a different way of understanding the various terms that appear in Einstein's equations, both on the left and the right-hand side. So are there any questions before I continue? I haven't done anything yet, so maybe there's not any need for questions. Okay. So what is the principle that we would like to use in order to determine the equations of motion of general relativity? Well, we would like to use the least action principle. So our goal is to write down an action for general relativity and to derive the equations of motion by minimizing this action. This action will be a functional of the metric of space-time, and we wish to minimize it with respect to the metric. And the minimization condition will turn out to be a second-order differential equation for the metric. And this will be the equation of motion of general relativity. And what we'll see is that there is essentially a unique choice for the action of general relativity, subject to some basic principles. And this variation will then lead to Einstein's equations. And it will also allow us to understand precisely one very useful way of thinking about the stress tensor. So, as I mentioned last time, so far in your lives as physicists, you've encountered action principles, and you found them computationally quite useful, but you've probably only really thought about them deeply in the context of particle mechanics, for example, where the dynamical variables are functions of time, but not functions of space as well as time. So, for a single degree of freedom, for example, which is a function of time, but not of space, which we might call q of t, then the action will typically take the form integral dt times some function called the Lagrangian, which depends on q and its first derivative. But if we are dealing with a theory of physics where we have not one degree of freedom that is a function of time, but rather a degree of freedom which is a function of both space and time. So, for example, if we had a metric g mu nu, which is a function of space and time, then the appropriate generalization of the action principle to a field theory will involve not an integral dt, but rather an integral d4x of some quantity, which we will call a Lagrange density, in analogy with the Lagrangian of particle mechanics, which depends on g and its derivatives. So, I think it's worth understanding a little bit why it is that action should be written as integrals d4x. One way of understanding why action should be written as integrals d4x rather than integrals dt is that in special relativity, there's no time and space are supposed to be treated on equal footing. So it doesn't make sense to write down a physical principle which singles out time as being special in some way. And so dt, the measure factor that appears in the action principle for particle mechanics, isn't something that's invariant under the symmetries of special relativity, whereas d4x is. So yes, there was a question.
Does the Lagrangian density
No, that's okay.
also depend on the space variables and space-time variables like p and x?
It could. Depending on what sort of principles you wish to impose. So remember that if in normal particle mechanics, if the Lagrangian density has an explicit t-dependence, there's no conserved energy. You could write down field theory Lagrangians for sure, which have some dependence on x mu, t or x, But then you would have to work out the implications of that. That's certainly something you could consider. Yes, but there was a question back there.
Is that quadruple integral?
Exactly. This is a multi-integral over all four of the space-time variables. Any other questions? Okay. So, the question then is, what is the natural action for general relativity? And what sort of principles should we impose so that the variation of the action will give us some sensible field equations for general relativity? So as a little homework problem last time, I asked you to imagine and think, based on the general physics principles you know and that you have learned in this class, what would be the most reasonable choice for the action of general relativity. And so now is your chance to see if you are as smart as David Hilbert or Albert Einstein, who did correctly guess the action principle for general relativity. You had a few hints, which they didn't have. But let's proceed. So what sort of principles should we obtain, should we impose when coming up with an action principle for general relativity? Well, the first principle is that the action should be coordinate invariant. As you probably remember in our discussion of integration in curved spacetime, there are only certain types of integrals which are expressions that you can write down which are independent of the choice of coordinate system that one uses to write down. And so, in particular, what this first principle will mean is that the action should be an integral d4x of the square root of the absolute value of the determinant of the metric. I remind you that the determinant of the metric is negative, so minus g is positive, and its square root will be real. And then that needs to be multiplied by some function, which will be a scalar under coordinate transformations. This is the only sort of integral d4x which you can write down, which is coordinate invariant. So among the zoo of possible Lagrangians you could write down for the metric of spacetime, this one is preferred. This form is preferred. And the second principle that we wish to impose is that the Lagrange density that I have written down should involve only second derivatives of the metric, or only, let's say, only 0th, first, or second derivatives of the metric. Why is that? Well, just as in particle mechanics, your Lagrangian will only involve at most 2 time derivatives, which will imply that your equations of motion will only have up to 2 time derivatives. Likewise here, the Lagrange density that you write down should only involve quantities that are up to second derivative in the metric, so that your equations of motion are second-order differential equations. Just because all of the equations of motion in physics, as we usually formulate it, are second-order equations of motion. Now, there's a slight subtlety here, something which might be confusing you, which is that typically in particle mechanics, our Lagrangians are actually just first-order in derivatives of the dynamical variables. You know, the Lagrange density of a particle moving in a potential is 1/2 velocity squared minus some potential energy term. That involves only first derivatives of your dynamical variables. But you could always integrate that by parts so that it looked like it contained a second derivative term. So second derivatives are allowed when you write down action principles for dynamical variables. Okay. Now, hopefully you remember our discussion of curvature in general relativity. And you remember that there is a unique quantity that I can construct out of the metric, which has these 2 properties. It is a scalar which is constructed out of second derivatives of the metric. So what is that unique quantity? Well, that unique quantity is the Ricci scalar. So the Riemann tensor is the guy which packages all of the various second derivative terms in the metric. There's one possible tensor we can construct by tracing over two of its indices, and one possible scalar that we can construct by tracing over four of its indices. So what that means is the Lagrangian has to be proportional to the Ricci scalar, with some constant of proportionality that we're going to determine in a little bit. So the action, which I will now refer to as the Einstein-Hilbert action, is going to be a constant times the integral d4x root minus g times the Ricci scalar. This is a functional of the metric, which depends on the zeroth, first, and second order derivatives of the metric. And we would now like to derive the Euler-Lagrange equations, which are obtained by varying this to first order invariations of the metric and setting that variation equal to 0. Before I do so, let me pause and see if there are any questions. No, c is a constant that, remember, the speed of light is set equal to 1 in this course, because I'll never remember where all the factors of c go. So c here is just some constant, which we will have to determine later on. And we will determine it later on. Yes?
But I can't see it affecting the Euler-Lagrange equation.
It will not affect the Euler-Lagrange equations yet. Okay? Yes. Let's see. If you are bored during the next 5 minutes, I want you to try and figure out how we're going to fix C. Okay? This is a nice exercise. See if you can figure that out before I get to it. Any other questions? Got it? No. Okay.
Shouldn't Lagrangian be invariant under multiplication by constant?
Yes, that was the point. So, as was just pointed out, if you write down the equations of motion coming by varying this action with respect to the metric, those equations will be independent of C. So then you have to ask yourself, is there some other principle that we're going to use, perhaps 1.5 pages from now, which will allow us to determine C? That's what you need to ask yourself. Okay. Any other questions? Good. Okay. So, to minimize this, or more precisely speaking, to extremize this, so this is a functional of metrics, and we wish to vary the metric and ask when the action obtains a local maximum or minimum. What we need to do is vary g mu nu so I'll take g mu nu to g mu nu plus delta g mu nu, where delta g mu nu is some small variation of the metric, and then we compute the variation of the action to first order in this small variation and set it equal to 0. Okay, so let's go ahead and do that. Now, let me write out this action a little more explicitly. So we have a square root of minus g, an inverse metric g mu nu, contracted with the Ricci tensor r mu nu. And the question that we need to ask is, how do these three terms, the square root of the determinant of the metric, the inverse metric, and the Ricci tensor vary? As we vary the metric, we'll need to compute their variations to first order in variations of the metric. So there are three different computations then that we'll need to do to look at how these three terms vary. Two of those computations will be easy and one of them will be hard. Right? Computing the variation of the Ricci tensor is actually a rather difficult thing, but we'll burn that bridge when we come to it. Okay. So let's first ask about the variation of the inverse metric. So let's imagine that we're taking g mu nu to g mu nu plus delta g mu nu. And let's compute first the variation of the inverse metric. That's the easiest one. Okay, so how do we compute the variation of the inverse metric? Well, what is the equation which defines the inverse metric? Well, it's the equation which says that the inverse metric is the inverse metric, namely that the inverse metric is the inverse of the metric. Okay, so let's imagine computing this the variation of this equation as we vary g mu nu to g mu nu plus delta g mu nu. So I'll call the variation of the inverse metric delta g mu nu with two upper indices, so that under the variation of the metric, the variation of the inverse metric is determined by this equation. Okay? All I'm doing here is I'm saying that if you vary the metric, then the variation of the inverse metric has to be such that the g upper mu lambda plus delta g upper mu lambda is the inverse of the varied metric. And we're only going to work to first order in our variation, so we can keep only the terms in this that are linear in the variation delta of the metric. And what do we get? Well, there's a term where this first term multiplies that first term, which just gives me the delta mu sigma, which I will subtract from both sides of this equation. And the terms linear in the variation will be one term involving the variation of the inverse metric times the metric, and the other involving the inverse metric times the variation of the metric. And this then is an equation which we can solve in order to write the variation of the inverse metric in terms of the variation of the metric. So how are the variation of the metric and the variation of the inverse metric related? Well, in fact, what I will do is I will just multiply both sides of this equation by the metric in order to lower this mu index here. And I'll write down an expression for the variation of the metric in terms of the variation of the inverse metric. So what do we have? We have g, the variation of g lambda sigma is going to be equal to minus g lambda alpha delta g alpha lambda. Let's call this delta g alpha beta g beta sigma. So I've relabeled my indices here a little bit just to make things clear, because I was summing over lambda in both of those terms. So I called lambda over here beta, and then I multiplied through by a metric g lambda alpha this equation. So this is the equation which relates the variation of the metric to the variation of the inverse metric. And in fact, when I write down my variation of the action, I could either write it in terms of a variation of the metric, or I could write it in terms of a variation of the inverse metric. And actually what I'm going to do is I'm going to work in terms of the variation of the inverse metric for reasons which will become clear in a few minutes. And this is the expression which tells me the variation of the metric in terms of the variation of the inverse metric. Is that clear? Any questions on that? Okay, good. No questions because it's crystal clear, and no questions because it's like 7 in the morning or something ridiculous. Okay, it's actually 9:30. It just feels like 7. Okay, so let's go ahead and compute the variation of the determinant of the metric. So we need to compute the variation of the square root of the determinant of the metric under g mu nu goes to g mu nu plus delta g mu nu. Okay. Well, in order to compute this, I'm going to use a little bit of a trick. So let me remind you, as most of you have probably learned at one point or another in your lives, that the determinant of a matrix is equal to the exponent of the trace of the log of a matrix. So you guys have all presumably seen this before. And this equation is extremely useful because exponents and logs are things that are very easy to take derivatives of. So if g is the determinant of the metric, then if I were to take the derivative of the determinant of the metric, or the variation of the determinant of the metric, then all I need to do is take the variation of e to the trace log of the metric. And what is the variation of e to the trace log of the metric to linear order in deformations of the metric? Well, it's e to the trace log of the metric times the variation of the trace of log of the metric. So, otherwise known as the determinant of g times the variation of the trace of the log of the metric. Now, taking the log of the metric is something that you don't really want to do every day. The logarithm of a matrix is defined by a formal power series expansion, but the advantage of that formal power series expansion for the log of a matrix is that it has the same property when you take its derivative as the normal logarithm of a number. So what is the derivative of the log of a matrix? Well, it's just the inverse of the matrix. In the same way that the derivative of the log of x is just the inverse of x. So this is g times the inverse metric times the variation of the metric. Or, if we wanted to go ahead and use this expression up above, you see that if we were to write that in terms of the variation of the inverse metric, we would just get a minus sign. So that the variation of the determinant of the metric to first order in the variation is just the determinant minus the determinant of the metric times the trace of the variation of the metric. Is that argument clear? Any questions on that? Yes?
When you're taking the trace of the log of the metric, doesn't taking the trace have an inverse metric built into it somewhere to use variation? I guess.
I understand what you're saying. The correct way that I should interpret this is when I take a trait. You remember the correct way, the tensor that actually, this equation that I wrote was a little imprecise, in the following sense. The tensor that actually transforms like a matrix is not something a 0-2 tensor, but a 1-1 tensor. There you take traces with respect to the Kronecker delta symbol, just by literally contracting indices. So I really need to talk about raising one of the indices and tracing with the Kronecker delta symbol, which doesn't have a variation with the metric. Good question, though. Yes. Any other questions? Yeah, I mean, this is an awfully slick derivation. I have to admit it. This is one of those derivations that you may want to sit quietly and think about for a little bit. There's another slight subtlety here. Okay, I don't want to mention it. Nobody asked, so I won't mention it. Yes, this is a derivation that is worth thinking about carefully. Yes?
What is that other slight subtlety?
Well, if you can't think of it, I'm not going to tell you. No. The slight subtlety is that when you take the derivative, so you need to use the fact that a matrix and its inverse commute when writing this down. In particular, it could be g mu nu times the variation of g mu. It could be the trace of, it could be g mu nu times, g upper mu nu times the variation of g mu nu, or it could be that in the other order, but those are actually the same thing. So, yes. You need to be careful sometimes when taking, or another way of saying that is that when taking the derivative of a matrix, you need to be careful that the matrix and its derivative might not commute. And so when you take a differential equation that's true in for functions, like the derivative of the log is 1 over the matrix, you need to be careful that equation might not precisely be true because the matrix equation might have some ordering of the matrices that's non-trivial. But in this case, as you can see, everything is just fine. Okay, so this is the variation of the determinant of the metric. So what is the variation of the square root of minus the determinant of the metric? Well, this is just the chain rule. So what do you get? You get 1 over the square root of minus the determinant of the metric times the variation of, there's a 1/2 times 1 over the square root of minus the determinant of the metric times the variation of minus the determinant of the metric, which is g times g mu nu delta g mu nu, which is just minus the square root of the minus determinant of the metric times g mu nu delta g mu nu. So that's the guy that appears in the equations of motion, because it's the square root of minus the determinant of the metric that is appearing in our Lagrange density. Okay. I lost a factor of 2. Thank you. Okay, so those are the two easy terms. Now what we need to do is compute the variation of the Ricci tensor. And this is where a miracle occurs. Because it turns out that the variation of the Ricci tensor is a total derivative. So it's equal to the covariant derivative of something. And I won't tell you what that something is. Here, let's write it this way. But what does it mean that it's a total derivative? What it means is that it doesn't contribute to the equations of motion. If you add a total derivative to the action, it won't contribute to the equations of motion. Because you could integrate it by parts and write it as a boundary term. Or you could use Stokes' theorem and write it as a boundary term. And so remember that when you write down action principles, you're always fixing the value of your degrees of freedom at the boundary. So you'll be fixing the metric out at the boundary, and so a total derivative won't contribute to the variation of the action. Now, if you wanted to, we could go through a very long and convoluted proof of this fact. It involves first the computation of the variation of the Christoffel symbol, and then the computation of the variation of the Riemann tensor, and then from that the computation of the variation of the Ricci tensor. I won't bother going through that derivation. I will just use this fact and refer you, for example, to our lovely textbook if you wish to see the proof of this. It's not too terrible. It's not the sort of thing that you want to do too early in the morning, however. Or maybe you want to get it over with early in the morning, if that's the sort of person you are. But we can put this all together. And so what was the Einstein-Hilbert action? Well, it was a constant times the integral d4x, root g, g mu nu, r mu nu. So the variation of the Einstein-Hilbert action, to first order invariations of the metric, what will that be? Well, it'll be the integral d4x of the square root of minus g times, first we have the r mu nu times the variation of the inverse metric, just varying this guy. Then we have this term here, so that the variation of the square root of the determinant of the metric is minus 1/2 times the metric times the variation of the metric. So we have minus 1/2 the Ricci scalar, which is just this guy here, times g mu nu, delta g mu nu, plus a total derivative. So, neglecting this total derivative term, which doesn't contribute to the equations of motion, what is this? Well, it's r mu nu minus 1/2 r g mu nu times delta g mu nu. And this is the guy which needs to be set equal to 0 for an arbitrary variation of the metric in order to extremize the action with respect to the metric. So the equations of motion, therefore, which come from extremizing the metric, are just Einstein's equations in vacuum. So the variation of the metric with respect, the variation of the action with respect to the metric, which is something that I'll abbreviate with the symbol delta S by delta G mu nu. So this is the variation of S with respect to G mu nu. What is that? Well, that's r mu nu minus 1/2 Ricci scalar times G mu nu, otherwise known as the Einstein tensor. And so simply setting the variation of S with respect to G mu nu equal to 0 gives the Einstein's equation in vacuum. I should mention one bit of notation here. So I chose to write the variation of the action in terms of the inverse metric rather than the metric, because the variation of the metric is a 0-2 tensor, and the variation of the inverse metric is a 2-0 tensor. The variation of the action is a scalar, so the thing which is contracted with the inverse of the variation of the inverse of the metric will be a 0-2 tensor. So that's why when I write the variation of the action with respect to the inverse metric, I get something with two lower indices. And the variation of the action with respect to the metric would have given me the equation of motion with two upper indices rather than two lower indices. Now, the physical content of those two equations is the same, but we're used to writing equations of motion with lower indices, and so that's why I've written everything in terms of the variation of the action with respect to the inverse metric. So you can see here that we're using the same rule that I introduced earlier, which is that when you have an upper index in the denominator of an expression involving derivatives, such as the one that I have written here, it should be treated as a lower index. So the delta G upper mu nu appears in the denominator of the variation of the action, and so that's treated as an object with two lower indices. And indeed, you can see that it's a 0-2 tensor, namely the Einstein tensor. Are there any questions on this derivation? There are a lot of rather technical steps that I slightly skipped over in this derivation. Most importantly, the proof that the variation of the Ricci tensor is a total derivative. I really just want to emphasize the basic structure to you and not waste all that much time doing computations. But if you're interested, I encourage you to go and work through the derivation yourself, possibly with the help of the book, if you want to see that the variation is a total derivative. Any questions? No questions? Okay. Well, this was all well and good. But what we really want to try and do is get the full Einstein's equations, including the source term on the right-hand side. So the question we now ask is, what about the full equations of motion, where we have some sources, namely some matter which is present, which will act as a source for the curvature of space-time? Well, in fact, that's very easy to do. It's almost trivial, given what I have told you, to understand now how to couple general relativity to matter and understand how that affects Einstein's equations. So the full action, so let's say that we have some matter, and we wish to understand the full action, not just of general relativity, but of general relativity plus some other stuff. Well, the full action will be the Einstein-Hilbert action with this mysterious constant that we have not yet fixed, plus some other action that I'll call SM, which will involve all of the various matter that's present. So M here tells us that this is the action which is describing all of the other stuff which is not just general relativity and not just involving the metric of space-time. Well, in order to write down the matter action, we're going to need to use the metric of space-time. The action of any theory that we're studying will involve, in various ways, the metric of the geometry in which we're writing that action down. So the equations of motion that are obtained for the metric, then, are obtained by varying both of these two terms in the action with respect to the metric. So the equations of motion are found by setting the variation equal to 0 when g mu nu goes to g mu nu plus delta g mu nu. So I remind you, as we saw above, that, so I actually was a little sloppy here. There's actually a factor of the square root of g here. So 1 over the square root of minus g of the variation of the action is equal to the Einstein tensor. So if we were to compute 1 over the square root of minus g of the variation of the action with respect to the inverse metric, what would we get? We would get this constant c times the Einstein tensor plus something else, which is 1 over the square root of minus g times the variation of the matter action with respect to the inverse metric. So what does that tell us? That tells us that the equation of motion says that g mu nu is equal to minus 1 over c times 1 over the square root of minus g, the variation of the action with respect to the metric. Now this is starting to look good, because what are Einstein's equations in the presence of matter? Well, they're the statement that g mu nu is 8 pi times Newton's constant times the stress tensor T mu nu. So now I need to tell you one deep, remarkable fact. And this is a fact which I will not prove to you. But if you like, you could simply take this fact as an alternate definition of the stress tensor. For a general system, the stress tensor is proportional to the variation of the action with respect to the metric. It's minus 2 over the square root of the determinant of the metric times the variation of that action with respect to the inverse metric. And again, I vary with respect to the inverse metric if I want to get the stress tensor with two lower indices, and I would vary with respect to the metric to get the stress tensor with two upper indices. That's a pretty remarkable statement. This gives you a completely different way of understanding the stress tensor, and we'll spend probably the remainder of this class using this to understand the stress tensors of various matter systems. But before I do so, I should just point out that this tells us what the constant is that was appearing as the coefficient of the Lagrangian of general relativity. So it tells us that this constant is 1 over 16 pi g. So that the action of general relativity coupled to some arbitrary matter system is 1 over 16 pi g times the Einstein-Hilbert action plus the action of the matter system. And this action will depend both on the metric of spacetime as well as on whatever other degrees of freedom describe the matter that we're studying. For example, this matter action could be the matter of the standard model of particle physics, which is a very complicated action. It could be the action of electromagnetism, which is rather simpler, or it could be some other action. So this fact that the variation of an action with respect to the metric gives you a stress tensor could be thought of as an alternate definition of the stress tensor. And in fact, it gives you a very slick way of computing the stress tensor for your favorite matter systems. So this gives us an easy way of computing the stress tensor of an arbitrary matter system. So, how would that work? So, maybe I should pause here and see if there are any questions before continuing. So, the fact that the variation of an action with respect to the metric is equal to the stress tensor as I defined it earlier, that's not something that should be obvious to you. What I'm going to do now is use this prescription to compute the stress tensor of a variety of systems. In particular, I'll compute it for electromagnetism, and then you could go ahead and check that this quantity that I compute for electromagnetism will agree precisely with the quantity that you encountered in your electromagnetism classes when you wrote down the stress tensor of electromagnetism. Let me also ask you the following question, just to see if this will be a little test to see if you guys have really internalized this fact. So the stress tensor is the variation of the action with respect to the metric. And if there's one thing that we know and love about stress tensors, it's that they should be conserved. That the covariant derivative of the stress tensor contracted with two of the indices should be equal to 0. So one thing that I encourage you to try and do is to try and prove using this formula that the stress tensor, as we have defined it using this equation, is conserved. That's actually a clever little exercise. If I had been thinking carefully, I would probably have assigned that as an exercise on a problem set. So I want you to think for a minute about how you might prove that. It's not entirely obvious. I'll give you a hint. I'll let you guys try and work it out on your own. But the hint is that you need to use the fact that the metric is covariantly constant, and that any derivative of the metric is going to be equal to 0. Okay, I won't spoil the surprise for you. Okay, are there any questions before I continue? Okay, so how will we use this to compute the stress tensor of an arbitrary matter system? Well, let's just consider some system and this matter that I would like to consider will include some fields. So, for example, you could have electromagnetism, which is described by a set of 4 fields that are packaged into one form, a mu. Or you could consider some more exotic type of matter, which involves a scalar field. Or you could imagine some other even more exotic types of matter involving spinor fields, such as those that describe the matter content of the standard model, or anything else that you like. I should emphasize that this procedure works only when we consider field theories, because it is field theories whose Lagrangians are scalars which is consistent with the principles of special relativity. So in your vanilla mechanics classes, you encountered Lagrangians which were integrals only dt, but you really should, in special relativity, be considering Lagrangians which are integrals d4x, which means that you need to be integrating some things which are local scalars, which are scalars under coordinate transformations, And the appropriate things that can be used to form scalars will themselves be functions of points in space-time, namely they will be fields. So when you're considering relativity, the appropriate sort of matter to consider is something which is built out of fields. Okay, so let's imagine that we have some matter system which is built out of some fields, say the electromagnetic potentials. So how do we compute the stress tensor? Well, the first thing that we do is we write the action in special relativity, and this will be the action which gives us the correct equations of motion of the system when we vary with respect to those fields. So this will be whatever action when we vary with respect to a mu, for example, would give us Maxwell's equations, or would give us whatever the correct equations of motion are. And then we covariantize this action according to the principle of minimal coupling as usual. So the integral d4x will become an integral d4x square root of minus g. Every partial derivative that appears in the action will become a covariant derivative, and every appearance of the Minkowski metric will become an appearance of the curved metric. And so that means that the actions of these fields will depend in some complicated way on the metric g mu nu. And in order to compute the stress tensor, we just need to vary with respect to the metric. I guess WRT stands for with respect to the metric. And I think it's truly remarkable that this procedure for computing the stress tensor agrees precisely with the previous definitions of the stress tensor as I have defined it. So what I would now like to do is work out a few different types of stress tensors for different sorts of matter theories, and they're special matter theories that we will come back and revisit later on in this class. But before I do so, let me pause and see if there are any questions. No questions? So far, what I've said about varying with respect to the metric might seem to be a little abstract. So it's perhaps useful now to work through a series of examples in a little bit of detail so you can get a feel for exactly how this goes. So let me now start with an example. And in some sense, this example is completely trivial. And in some sense, this example is the most complicated thing that we will encounter this semester. So let's consider the example where the Lagrangian is equal to a constant. So in special relativity, and in your normal mechanics experience, you are surely familiar with the fact that if we added a constant to the action, if we added a constant to the Lagrangian, it would not affect the equations of motion. So adding a constant to the Lagrangian does not affect the equations of motion. However, there's another way of saying this. So in your standard mechanics classes, if you just have a single degree of freedom, which is a function of time, then the Lagrangian is the kinetic energy minus the potential energy. So adding a constant to the Lagrangian would just correspond to shifting the potential energy of your system. And as you know, the equations of motion are unchanged if you shift the location of the zero of your potential energy. If you shifted your potential energies all by a constant, physics would not be affected. Okay. But what happens in general relativity? In general relativity, your Lagrange density is not a constant. So your action is not a constant because a constant is not something that you can integrate over d4x in a covariant manner. You can only integrate the square root of minus g times a constant. So I'll just give that constant a name. I'll call it lambda. That's as good a name as any. And I'll even introduce a factor of 1 over 8 pi g along with a minus sign to make my life easier. So here lambda over 8 pi g is a constant, which is the thing that we're imagining adding to the Lagrange density, which would correspond to some overall shift in the potential of whatever systems we're studying. And the important point is that in order to correctly couple this constant to gravity, we need to include a factor of the square root of g there. That's going to mean that the stress tensor is not equal to 0. So this constant is going to affect the equations of motion of general relativity. So the total action, which is the Einstein-Hilbert action, let me call this SM so that we'll think of this as a matter action. It will be the integral d4x times the square root of minus g times r minus 2 lambda. And there's a 1 over 16 pi g out front. So what is the equation of motion? Well, the equation of motion is r mu nu minus 1/2 g mu nu r. That's just the Einstein equation. And that's equal to the variation of this matter action with respect to the metric. And what is that variation? Well, you just need to calculate the variation of this guy here. That's the computation that we did before. The variation of the square root of the determinant of the metric is equal to the square root of the determinant of the metric times g mu nu delta g mu nu. So that means that the stress tensor is just proportional to g mu nu. And in fact, I introduced this factor of 2 here in order to get rid of that factor of 2 in the definition of the stress tensor. So this is just minus lambda g mu nu. So this is, in a sense, the simplest kind of matter that you could ever imagine adding to the action of general relativity. It just corresponds to adding an overall constant to the action in special relativity and then coupling it to general relativity using the usual principle of minimal coupling. So this lambda has a name. It's called the cosmological constant. It's also referred to as vacuum energy. We encountered the cosmological constant last lecture when we considered stress tensors, because in fact this cosmological constant matter is an example of a perfect fluid. Remember, it's the perfect fluid with negative pressure. P equals to minus rho, where rho is the energy density. That was just the statement that the stress tensor was proportional to the metric. And now we see that, in some sense, it's the most natural possible thing that we could include as a matter source in general relativity. But there's also a sense in which It's the most unnatural thing that you could imagine having in general relativity. Why is it so strange? Well, in special relativity, as I mentioned, physics is insensitive to adding an overall constant to the Lagrangian, or to the potential energy. So, for example, when you're doing standard mechanics or special relativity, it's usually typical to normalize your potential so that, for example, the minimum of the potential would happen at v equals to 0. Or in the quantum mechanical language, it's typical to normalize your energies so that your ground state would have energy equals to 0. That's what it would mean in the quantum mechanical sense. And that's just fine in quantum mechanics, unless you start thinking about general relativity. Because what we're now discovering is that in general relativity, the energy of the ground state is observable. It appears in Einstein's equations. So that's why lambda is sometimes called the vacuum energy. So lambda is thought of, if you want to use the quantum mechanical language, the energy of the ground state. So you could then ask the ground state of what? Well, it's the ground state of the Hamiltonian that describes all of the matter in the universe. So actually, computing the value of lambda is a very, very difficult thing to try and do. So, and it turns out, I mean, this is, I think, one of the most fascinating stories in physics, and it's a story which has not finished, so I can't tell you what the end of the story is because I don't know the end of this story. But the fact is that even though this is invisible in special relativity, it's visible in general relativity. Now, if you were to read a general relativity textbook written before 1995 or so, there's a good chance that they wouldn't even bother discussing the cosmological constant. Because everyone assumed that even though we had no way of calculating it based on first principles from quantum mechanics, it was almost certainly equals to 0. Okay, why did people assume that the cosmological constant was equal to 0? Well, let's imagine trying to compute it in some quantum mechanical way. You know, what's the prototypical example of a system which has a non-zero ground state energy? Well, the harmonic oscillator has a ground state energy which is 1/2 h bar omega, where omega is the frequency of the oscillator you're studying. And if you look at any quantum field theory, it looks like a bunch of oscillators. So as you know from your mechanics classes, everything looks like oscillators. Everything is an oscillator. Physics is that subset of human experience which can be reduced to coupled harmonic oscillators, right? So if in any field theory, if you look at, for example, the quantum fluctuations of the electromagnetic field, for example, that looks like a bunch of oscillators. Okay, it's an infinite number of oscillators because there's 1 degree of freedom for every point in space-time. It's still just a bunch of oscillators. So it has some non-zero vacuum energy, according to the basic idea that a harmonic oscillator has a non-zero vacuum zero-point energy, which is 1/2 h bar omega. So if you start looking at the sorts of quantum mechanical systems that we observe around us, not just the electromagnetic field, but all of the various particles that appear in the standard model of particle physics, you quickly see, you start adding up all of these ground state energies, and you see very quickly that you get a very large answer. Now, some of the systems that we have in the Standard Model give you positive contributions to the cosmological constant or to the vacuum energy. Some of them give you negative contributions to the vacuum energy. But unless a miracle occurs, you would expect the scale of the cosmological constant, the scale of the vacuum energy, to be set by whatever particle physics energy scale you have. And it turns out, as you will show on the problem set that I handed out on Monday, that this leads to a value of the vacuum energy, which is in stark contrast to the equation, to observations. So, in fact, as we will see in our discussions of cosmology, and in fact, as you will see on the next problem set, the presence of a cosmological constant has drastic implications for the types of solutions that you have to the equations of motion of general relativity. In particular, the presence of a cosmological constant will make space-time either want to expand at an exponential rate or contract at an exponential rate. Now, in fact, the universe is expanding. It's doubling in size every 10 billion years or so. And so you might say, well, that sounds pretty good. Let's compare that to the expected doubling rate that you would get if you start adding up all of the vacuum energies for the particles of the Standard Model. Well, what is the typical time scale associated to a particle, in an electron, say, moving around in an atom? It's a hell of a lot shorter than 10 billion years. So if you were to go through this calculation and you were to set lambda equal to the typical particle physics energy scale, you would find that the universe would have to be accelerating at a rate where it would double in size every, I don't know, nanoseconds, something like that. Whatever the typical light crossing time is for some particle physics atomic system or nuclear system. It depends on exactly what sort of model you're talking about. But I think it's fair to say that this discrepancy between the 10 billion year doubling rate that we observe and the microscopic doubling rate that you would predict from your theories of quantum mechanics and particle physics is perhaps the single greatest discrepancy between theory and experiment that we have in physics today. That's why I say that the cosmological constant is both the simplest type of matter that you could consider in Einstein's equations, but also the most confusing. So if it were 1995, we would all be wearing flannel shirts and corduroys or something like that. And we also probably would not be discussing the cosmological constant. Because for a very long time, it was assumed that because the quantum mechanical computation of the cosmological constant gave you an answer which was so ridiculously large, it had to actually be zero, right? There had to be some mechanism that we didn't quite understand, which would set the cosmological constant equal to zero. And so for a very long time, people studied cosmology and general relativity and so forth, assuming that the cosmological constant was exactly zero, because there was something that we didn't quite understand either about quantum mechanics or particle physics, or maybe there was some mechanism in general relativity which would dynamically relax the cosmological constant to zero. There was some sort of mechanism we didn't understand which set it equal to zero. And this was a perfectly reasonable and happy state of affairs for several decades until in the mid-90s something rather dramatic happened, which is people actually started doing observations, astronomers started doing observations, and they realized that the evolution of the universe looks a hell of a lot like there's a cosmological constant. In fact, the current, I'm getting ahead of myself here, but the current best guess for the matter content of the universe says that something like 70% of the matter content of the universe is in fact vacuum energy. The rho, which describes the matter density of the vacuum, accounts for the majority of the energy density in the universe. We'll discuss this in much more detail in our study of cosmology, but I think it's fair to say that this was a shock to almost everybody. And the repercussions of this are still being worked out in the physics community. It means that those of us who are interested in general relativity have a very big problem to discuss, which is the problem of why the cosmological constant, not only is it so very small compared to the quantum mechanical expected value, but we also have to explain why it's so small but non-zero. I mean, I'm not going to answer this question for you. There are a variety of different proposals on the table. I think it's fair to say that none of them are completely accepted, and they each have their advantages and disadvantages. But I think at this point, it's the time in the history of physics where we can no longer ignore the cosmological constant. We ignored it for 70 years or so, and that time, unfortunately, it's time to grow up and accept the fact that either the cosmological constant or something like it is probably present in the action of the universe. So I say, or something like it, because as we will see when we consider other types of matter content that could appear as sources in general relativity, there are other things that look a lot like a cosmological constant. We'll discuss this next time when we encounter scalar fields as another example of source terms in general relativity. And as we'll see, there are other sorts of matter terms which we can add which look approximately like a cosmological constant in certain circumstances. And so it might be that lambda is actually zero for some as yet undiscovered reason, but that there is other sort of matter in the universe which is causing this effect that we're attributing to the cosmological constant. So I think if I were to summarize this discussion of the last 10 minutes, I would probably just have to say it's poorly understood. It's worth also making a bit of a comment at this point. So the equation of motion in the presence of a cosmological constant is rather simple, and it can be made even simpler. If you take the trace of both sides of this equation, what you'll see is that R, so if you take the trace of the left-hand side of the equation, we get minus R, as we have seen several times already, and the trace of the right-hand side is 4 times lambda, so R is minus 4 lambda. So that means that R is non-zero. The Ricci scalar is non-zero, but it is equal to a constant. And so that the Ricci tensor will be equal to a constant times the metric. So if you're studying solutions of general relativity, where the only matter content is a vacuum energy, or something that looks like it, then the equation of motion just says that the Ricci tensor is not zero, but is rather proportional to the metric. So I remind you that the vacuum Einstein equation said that the Ricci tensor was equal to 0. This is the next simplest generalization of that. And geometries which satisfy this equation of motion, R mu nu is proportional to G mu nu, are relatively simple compared to other more complicated solutions of general relativity. And they have a name. They are known as Einstein spaces. in fact, they're known as Einstein spaces because Einstein himself considered the cosmological constant as a very natural sort of matter term that one can include in the equations of motion of general relativity. And in fact, he included the cosmological constant because he believed that the universe was static, and he understood that if you have some positive matter density, that will make the universe want to either expand or contract. And so you need to add some other term to try and cancel it. He wanted to cancel it using the cosmological constant. That turned out not to work. And he then proceeded to declare that the cosmological constant was the biggest mistake of his physics career, and he decided to set it equal to 0 from then on. I think it's one of the great ironies of 20th century physics that the 20th century began with Einstein discarding the cosmological constant, and then it ended with the cosmological constant being resuscitated by astronomical observations. And so, in fact, Einstein, as was often the case, was many decades ahead of his time, even though he didn't know it. So that's probably a good place to end. I will see you tomorrow at 4 p.m. in the piano room.